Hello. Hello everyone. Okay, shall we start? No. So let us start again from the first. So we would first move into the definition of groups by giving some motivation. So yesterday we saw about an equation x plus 5 equal to 0. So what we did is, maybe you can view it this way. X plus 5, I added an element here and added an element here, which is going to be the same. Now we just switch the brackets and we got an element which when added with any x gives us back the same x. So this x plus 0 will result in x and this will be minus 4. So what we did was, given any element, we are searching for another element which when added with it gives us something like 0, which has a property that when you add any element with 0, you get back the same. Right? So we define what is a group now. So before defining a group, we will specifically see what is a binary operation. Star is said to be a binary operation on G when if suppose this is G, if we take any two elements from this set A and B, and when we operate these two elements, we get back an element in the same set, say some C. And we are going to denote this not by C, we are going to denote this by A star. So we are taking two elements. So to denote that, we will use G cross G, which is nothing but Cartesian product of G with itself. And we define this function from G cross G to G. Now we define it in such a way that star of A comma B is nothing but A star So for example, now so I think it is visible to everyone. Now, so closure and binary operation is they are not too distinct. They actually mean the same. That is, if star is a binary operation on G, says that G along with star satisfies the property closure property. That is, so we will list down all the four properties. Closure. So what it means is, so maybe we will use perfect quantifiers to denote this. Given any a comma b in G, a star b, the operation defined on G must belong to. Now, if suppose the set given to us along with the binary operation does not satisfy the closure axiom, then we need to find an a comma b in G such that a star b does not belong to G. So this is used to show that a given set and a binary operation does not satisfy closure axiom. So we will move on with this technique. So next one is associativity. So hereafter, while listing down all the properties, we will list down how to prove the property is not satisfied. We will also mention it along with how to prove the property is satisfied. Now, associativity refers to switching of brackets. That is, you can if we have three elements, then those three elements can be operated in uh, in whichever order possible. Whichever order in the sense, the first two elements can be operated first and then with the third, or the second and third can be operated and then it can be operated with the first one. That is, given any a comma b comma c in G, a star b star c must be equal to a star b star c. So if suppose for some set and for some binary operation star this is not true, then you need to find a b c in G such that a star b star c is not equal to a star b star c. Okay, so this is what you need to prove when we are going to say a given set and a binary operation does not satisfy the associativity axiom. So identity. What does identity refer to is when we saw the motivation part, we saw an element called 0. So what is the use of that element is when you add any element of the set along with when you operate any element of the set with that element, you get back the same element. That is, it pulls back to the same element. So given any a in G, a star e must be equal to e star a must be equal to a. That is, you need to find one e in G such that given any a in G, a star e must be equal to e star a must be equal to a. If suppose an element a set along with the binary operation does not satisfy the identity axiom, then what we need to prove is given any e in G, I can find given any element in G, I can find at least one element in G such that a star e is not equal to which is not equal to e star. So if suppose we need to show that a given set along with the binary operation does not satisfy the identity axiom, that is, it does not have an identity, then we need to show this. That is, take any element in G, we can find at least one element in G such that A star E and E star A, which are not equal to A itself. Right? Now, so let us move on to the fourth axiom, inverse. Inverse. So, inverse is, so it depends upon the previous property, that is the identity one. So, inverse, what it says is, given any A in G, given any element in the set, I can find another element in the same set such that A star B returns back to the identity element, which is nothing but again B star. That is, given any element, I can find at least one element B such that A star B is nothing but identity element. So we will denote this B by A inverse, but only when if you show this is unique. Because we are denoting an element as A inverse, there might be many B such that A star B is equal to E. So we will try to prove that this is unique, and then we will go into saying that this B will be denoted by A inverse. Now, if suppose a group does not satisfy, sorry, a set does not satisfy the inverse axiom, then what do we need to show is there exists at least one element in G such that given any B in G, A star B is not equal to identity. That is, at least one element, you can find at least one element such that when you operate it with any element in the set, it does not give us identity. Right? So, now, so this is what we need to show whenever you want to prove that the set along with the binary operation does not satisfy the inverse axiom. Now, these four properties gives a structure on the set G which depends upon the binary operation, and hence a set along with the binary operation which satisfies these four axioms is called a group. Okay. Now, there is one another property which not every group satisfies, but there are few groups which satisfies this property. We are going to number it the fifth property, which is the commutative property. That is, given any A comma B in G, A star B and B star A are equal. Given any two elements, it doesn't matter in which way you operate. That is what this refers to. That is, given any two elements, A star B and B star A are going to be the same. So if you want to prove a group is not commutative, then you need to show there exists at least one pair of elements in G such that A star B is not equal to B star. Fine. Now, we will look into few examples which we saw yesterday, and we will move on to some more examples. Okay. We will move into few complicated examples today. So maybe we will prove. We will first recall, say maybe natural numbers under addition does not form a group because it does not have the identity element. So maybe you can check, given any element, given any natural number, if you add with any other natural number, it is going to be again a natural number, but which is going to be bigger than the given two numbers. So it does not give back A again. That is, given any two natural numbers, A plus B obviously belongs to N. Closure is true. This operation, whenever on whichever set we define the usual addition, it satisfies the associativity. So associativity is true. But if we search for an element called identity, then it does not exist, because if suppose an element identity exists in natural numbers, then a, for given any a in n, a plus e must be a. So we know about addition. If you want a again, when you add an element with a, then this must be nothing but 0. But 0 does not belong to natural numbers. So natural numbers under addition does not form a group because it does not have the identity. Now, we'll move into Z. So maybe we will move into first check with the whole numbers under addition. Now, the problem with the natural numbers under addition was it does not have the identity element. So we tried to include the identity element into the set, and that set is nothing but the whole numbers. Now, this set we will obviously it satisfies the closure and associativity, because addition of any two whole numbers is again a whole number, and associativity is obviously satisfied. Now, it has the identity element, that is, I can find an element which is called 0 in W, such that given any whole number, a plus 0 is obviously a, because it is the property of 0 under addition. So we have found the existence of identity element. So maybe we will here we will put checkbox. Closure is true, associativity is true, identity is true. Now we need to check the inverse part. So maybe let us look into so we have shown that 0 is the identity element of this set. Now if I take any whole number, say for example 1, you need to find another element in whole numbers such that this must be 0. So that is what the inverse axiom says, that is, given any a in G, there exists some B in G such that A star B is equal to identity. So obviously the only possibility under this operation, 1 plus something must become 0. So this box can be filled only with -1. But -1 does not belong to whole numbers. So we have found one element for which if you add with any other element, it does not become 0 again. So 1 does not have an inverse. So inverse axiom fails. Okay. So what we progress in a logical way. First, we saw the basic set natural numbers. It didn't have identity, so we included the identity element. Now, when we saw the whole numbers under addition, it had the identity element, but it did not have the inverse. So inverse of any a in whole numbers will be nothing but -a. But -a does not belong to the set of whole numbers. So what we do is we extend the set. So we take the set of all integers under addition. Now we will put a checkbox whether it satisfies all the 5 axioms. 4. Now, obviously closure is true, because when you add any two integers, it is going to be again an integer. Okay. Now, next, associativity is the property of addition, the binary operation. So it is also true. So closure and associativity are true. Identity, this set as the identity element, because under addition, usual addition, 0 is the identity element and 0 belongs to integers, so identity is true. Now we need to check for inverse for every element. So given any a in z, we need to find some b in z such that a plus b is 0. So we need to fill in this b. We need to find a b such that a plus that b must be 0. Obviously, given any a, minus a, when you add a with minus a, we are going to get 0, and that minus a belongs to z. So for example, if a is minus 10, you can choose b to be minus of minus 10, which is nothing but plus 10. So minus 10 plus 10. This is going to satisfy the inverse axiom. That is, this is not just true for a equal to minus 10, this is true for any given a in the set of all integers, not just for one or two elements. Given any a in z, I can find what we call as minus a in z such that a plus minus a is 0. So it satisfies the inverse axiom. So this, the set of all integers under addition forms a group. So let us check whether addition satisfies the commutativity axiom, so that you can call it as an abelian group. So whenever you add any two numbers, any two, this is not just in integers. Under usual addition, when you add any two numbers, a plus b is always going to be equal to b plus a. For any a and b can be any numbers in any subset of real numbers. Can choose a and b from any subset of real numbers. So this satisfies this is actually a property of the binary operation, and hence this commutative axiom is satisfied, and hence this is not just a group. Integers under addition is an abelian group. Okay. So if you need any clarifications, please mention in the chat. Maybe we can proceed with next example. Okay. So let us proceed to the next subset of real numbers. Okay, so there is a question from Mahesh. Let the set be natural numbers. Define star to be a star b equal to a again. Fine. So you need to check whether it is a group. Okay, fine. Let us check. He has defined his own binary operation. So let us check whether it forms a group. N under star, where star is defined to be given any a comma b in G, a star b, this is natural numbers, a star b is defined to be the first element. Okay, fine. So closure is obviously satisfied, because given any a and b, a star b is defined to be given any a and b in N, a star b which is equal to a belongs to N, because you have taken a from N. So closure is satisfied. Now let us check the associativity part. Now let us consider three elements a, b, c in natural numbers. Now a star b star c will be, by our definition, a star b is a, and this is c, and this is going to be a. Now a star b star c, which is going to be a star b, which which is going to be A. So associativity is also satisfied. Now, let us check for the identity axiom. Now you need to find a natural number such that A star B is A. By our definition, any element is identity here. Any element is identity here. Fine. Now, so there is an issue here, I guess. Can someone find out what is the issue? Can you please mention it in the chat? Okay, fine. So for B, for given any A, say maybe we will take 1 to be our A, 1 star 2 is 1. Okay, there is an answer here. Good. So when we defined identity, we defined it this way. A star, identity. We defined it A star B must be, there exists E in N such that A star E equal to E star A is equal to A. Now, if suppose A will be B, these two are not equal. And hence, this is, we can choose this B to be any given natural number. These two are not going to be equal. If you choose A and B are not equal. Right? So, by definition, maybe we'll rewrite the definition, again write the definition of natural numbers such that given any A in natural numbers, A star E equal to E star A is equal to A. Now, if suppose we had found a natural number E in N, then A star E will be A, obviously. But E which is not equal to, where A is not equal to identity. If you had taken any other element other than identity, this is not equal. And hence the identity axiom is not satisfied. And hence this does not form a group. Hopefully it is streaming here. Fine. So let us move on to the next exam. So is there any other clarifications? Please mention it in the chat. Okay, good question. So there is a question from Mahesh. Does there exist a binary operation on the set of all natural numbers such that the set of all natural numbers forms a group? So there is a question. Maybe we should think of it. There is a possibility if we define the binary operation in such a way that it satisfies. Maybe we will discuss it later. I think there is a possibility. That is possible. That is possible. Now, so let us move on to the next example. So, next example, we will go into the set of all rational. So, maybe we will go for another example, but we will now shift the operation maybe. So, we will consider the set of all integers under multiplication. Now, this is the usual multiplication. It's the usual multiplication. Now, let us check whether it satisfies the properties. Let us have a checkbox. So, if we take any two integers, say A and B, its usual multiplication is again an integer. Obviously, AB belongs to Z. Now, associativity, it is the property of the binary operation. Multiplication is always associative. The usual multiplication in real numbers. So associativity, closure and associative is not an issue here. Now let us move on to the identity part. So we need to find identity. Since identity is satisfied, we can go on to check the inverse axiom. Now, given any A in integers, we need to find an element B in integers such that A star B is 1. That is under usual multiplication, AB must be equal to 1. Okay. So for this to be satisfied, given any A in Z, you need to find one another element B in Z such that AB must be equal to 1. So if we take, say for example, A to be 0, can you find an element 0 into 0 into, can you find one element such that it becomes 1? So we know that multiplication of a number with 0 gives always 0. So it will result in 0 and 1 are equal, and hence the element 0 in integers does not have an inverse. So we have found one element which does not have an inverse. So integers under multiplication does not form a group. Okay. So let us move on to the next example. So, and one more thing, in integers under multiplication, for 0 does not have an inverse. Also, if we take any other element other than 1 and minus 1, say for example, if we take 2 in Z, we need to find one B such that 2 into B is 1. So for this to be satisfied, B must be 1 by 2, which does not belong to Z. So whenever you choose an element, say 2 from Z, it does not have an inverse. So we have found another element for which the inverse does not exist. So what we do is we are going to overcome these two drawbacks in integers by by having a new set where there is no zero, and where given any element in that set, its multiplicative inverse exists. So what we do is we define the set to be the set of all rational numbers. We remove 0 from the set of all rational numbers. Under multiplication, let us check whether it forms a row. Right? Now we know given any rational number, it is of the form p by q. Clearly, q is non-zero, and since we have removed 0, p is also non-zero. Now, obviously, multiplication of any two rational numbers. Let us check. So, if we take p by q and r by s to be two rational numbers, non-zero rational numbers, then its multiplication is pr by qs, which is again a non-zero rational number. So, closure axiom is satisfied. So, closure axiom is satisfied. Now, associativity, the usual multiplication is always associative for any subset of real numbers. So associativity is always satisfied. Now we need to go check for an identity element. Let us take an element p by q in q difference 0, any random element. We need to find one element in the set of all rational numbers difference 0, such that whenever you multiply with that element, you get back p by q, and this must be from q minus 0. So this must be a rational number. So we choose this element to be 1. Now, clearly 1 belongs to the set of all rational numbers, because 1 can be written as 1 by 1. As simple as that. So this will be nothing but p into 1 by q into 1, which is equal to p by q. So we have found one element, 1. We have found an element, say 1, in the set of all non-zero rational numbers, such that p by q into 1 by 1 results in p by q again. So this is also true in the other way, that is 1 by 1 into p by q is equal to p by q. So identity axiom is also true. Now we need to find the inverse. Since q is a any element here is a non-zero rational number, p is non-zero, and by definition q is always non-zero. So we are going to define, given any p by q in q minus 0, we can find an element, say q by p in q minus 0. Clearly this belongs to q minus 0 because p and q are non-zero. So q and p are non-zero. Q by p is well defined. So by definition of our binary operation, p by q into q by p is pq. So maybe we can easily cancel it out, and we get 1 by 1, which is nothing but 1 are identical. So this is true the other way also. Here itself you can clearly check that p by q into r by s is equal to r by s into p by q, which is nothing but pr by qs. So commutativity is true, and given any element here, we have found an inverse. So it satisfies the inverse axiom also. Okay. So the one, why did we remove 0 here? The reason is we couldn't have defined the inverse for 0. if suppose 0 can be written as 0 by 1, so 0 is obviously a rational number. If suppose an inverse exists, you need to find 0 by 1 into some p by q must be equal to 1. Obviously, this is 0, left hand side is 0, and the right hand side will be 1. You cannot find an element which satisfies the left hand side and which satisfies LHS is equal to RHS. So, whenever you have a 0 here, it does not satisfy the given axiom, and hence we remove 0 and try to make it a root. So, the set of all non-zero rational number under multiplication will form a root. Now, the same thing holds for the set of all real numbers under real numbers difference 0. That is, you remove 0 from the set of all real numbers, and this again forms an abelian. So, you can verify. So, is there any clarifications? Please clarify if you have any clarifications, or if you need us to check anything, any set and binary operation to be a. So maybe you can try at home. So consider the set of all non-zero rational numbers and the operation to be division. Now please verify whether this forms a group. This is an interesting example where there is something which lies in this example which you will come to know when you try on your own. Okay. Now I will deal with one more example and maybe I will stop. Now, so choose a natural number n. It's a natural number. It's a natural number. Now we define this set to be, denote this set to be Zn, which contains 0, 1, 2, etc. up to n minus 1. Fine. So what this set is, so whenever you divide any natural number by another natural number, so not just natural numbers, whenever you divide any integer by a natural number, the set of all possible remainders are nothing but this set. This 0, 1, 2, etc. up to n minus 1. That is, whenever you divide an integer by n, the collection of all possible remainders are nothing but 0, 1, 2, etc. up to n minus 1. Now here we define an operation. On this set, we are going to define an operation Zn. We are going to denote this by plus n. How we are going to denote this or define this operation is a plus b is nothing but is defined to be some r where a plus b is congruent to r mod n, or else we can write it in another way where a plus b is equal to, this plus denotes the usual addition of integers. A plus b is equal to some qn plus r, where 0 less than or equal to r less than n minus 1. That is, to be stating it very simple, what we do is we take any two numbers from this set, we do the usual addition and divide it by the fixed natural number n. Whatever is the remainder we get, that is defined to be the a plus n b. That is defined to be a plus n b. So for example, consider we will fix a natural number. We will fix the natural number to be, say, n is equal to 4. Now Z4 will contain the set 1, will be the set 1 2 0 1 2. So if we take say 2 2 plus 4 3, this is nothing but, so we will compute it. So what is 2 plus 3, which is 5. Now we divide 5 by 4, the quotient is 1, the remainder is 1. So 2 addition modulo 4, we pronounce it as, we call it as addition modulo 4. 2 addition modulo 4 3 is nothing but 1. Maybe you can have a doubt whether it is the quotient one or the remainder one. So let us check with some other number. Say consider the number 3. So 3 addition modulo 4, 3 usual addition 3 will result in 6. Now divide 6 by 4, you get the quotient to be 1, remainder to be 2. So 3 addition modulo 4 3 is nothing but 2. Obviously this satisfies the closure property because we are collecting for given any operation, given any operation between any two elements, we are collecting the reminders. So obviously this set consists of all possible reminders, so closure is true. Associativity is again, it comes from the usual addition of integers. Also identity element 0 acts as the identity element because whenever you add any element with 0, you are going to divide the same element. And the inverse is the most crucial part here. Now let us consider 2. We need to find an element here which results in 0. So maybe we'll consider the element 1. Now which element when added with 1 in addition modulo 4 gives us 0. So obviously if you check 1 plus 1 will be 2. When we do addition modulo 4, it will result in 2 again. Also 1 plus 2, 1 plus 0 will be 1. So definitely it is not 0. 1 plus 1 is 2. Addition modulo 4, it is again 2. It is not 0. 1 plus 2 is 3. Addition modulo 4, it is again 3. Now 1 plus 3 is 4. So when you divide 4 by 4, your quotient is 1 and the remainder is 0. So the inverse of 1 is nothing but 3. So in general, for given any n, given any zn, if you consider the element x, where x is non-zero, for 0, since 0 is the identity element, it is its own inverse. For any non-zero element, if you need to find the inverse, what we do is we just find what is n minus x. So x addition modulo n minus x will be x. What we do is we do the usual addition, x plus n minus x. Usual addition, associativity is true in the usual addition of integers. So this will result in, and since it is commutative, this will result in n. So n when divided by n, you will get quotient to be 1 and remainder to be 0. So n minus x is the inverse of x in Zn. So this is true for any given n. So since it is commutative also, any Zn is an abelian. Okay. So I think I will stop here. If you have any clarifications, please mention it in the chat. So is there any clarifications? Okay. So I think we can stop here. Thank you. If you have any comments on this live session, please mention it. And thank you.